Hi everyone, welcome to one of our Math 111 lecture videos. This video is for section 2.1, which is about exponential functions. So first I'm going to review some rules of exponential notation. Exponential operations, right, arithmetic operations, is repeated multiplication. So instead of writing 4 times 4 times 4, I can write 4 cubed, and 4 times 4 times 4 is 64. Because of the way repeated multiplication works, if I do 4 times 3 times 4 times 5, I can write out that repeated multiplication, and I get 4 times 4 times 4 times 5 fours all multiplied together. And I have, I think that's not 5. Now it is 5 fours. So 4 times 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 4. That's 4 multiplied by itself 8 times, which is what you get when you add the exponents. So multiplying two exponentials adds the exponent. And that reminds me I should review some of our vocabulary. If I have 4 to the 3, I call 4 the base, and 3 is either the exponent or the power. So multiplying two exponentials with the same base, you add the exponents, so you add the powers. Now, I'm going through this pretty quickly. There are some review videos online to go through it in more depth, but if you have these in your notes and you bring something like this with you to remind you, I think that'll be a good starting point. Another reminder is multiplication and division are two sides of the same coin. So it would make sense if we have some kind of exponential notation for repeated division. Nobody writes something like 4 divided by 4 divided by 4 divided by 4 divided by 4. Nobody would ever write that, I hope. Instead, what we would do is we would think about multiplying fractions. So division by 4, repeated division by 4 is the same as repeated multiplication by 1/4. And so we can write that as 1 divided by 4 to the 5th. And if you remember from previous video, I told you I didn't like the inverse notation, and this is the reason for it. Mathematicians, instead of writing this fraction, which, by the way, as an aside, could be written as all of 1/4 to the 5th. But anyway, instead of writing 1 over 4 to the 5th, we write 4 to the minus 5. Means, right, 4 to the power 5 in the denominator, which is exactly 1 over 4 to the 5th. So negative exponents means a power or an exponent in the denominator. And the real reason mathematicians developed that notation is because it allows the other rules, like the one we just saw, to work. So if I were to take 4 times 4 times 4 times 4 times 4, and then I was to divide it by 4 times 4, we know the divisions will cancel and we end up with 4 cubed. But on the other hand, 4 times 4 times 4 times 4 times 4 divided by 4 times 4 is equal to 4 to the 5th divided by 4 squared, which you could write as 4 to the 5 minus 2. When you do division, you subtract powers. And the reason we write this as a minus 5 is because it indicates that it's subtracting the power. So dividing exponentials of the same base subtracts powers. The top power subtracts the bottom power. A couple more rules to refresh you on. What about an exponential followed by another exponential? What about 4 cubed and then I raise all of that squared? Well, let's go back to using our multiplication idea. That's 4 times 4 times 4 times 4 times 4 times 4. Because I have a 4 cubed, and then I multiply that 4 cubed by itself. Well, that's 4 raised to the 6th power, which so happens to be 4 raised to the 3 times 2. So an exponential raised to another power multiplies the powers. And really all we're doing here is we're keeping track of our exponential grammar, starting from one simple rule, which is that exponentials are repeated multiplication. We can develop these shorthands that allow us to do our exponentials a little more easily. Okay, moving on. Exponentials distribute across multiplication and division, but they do not distribute across addition or subtraction. And so I'll just show you what I mean by that. Let's take 3 times 2, and we're going to raise that to the 5th power. Well, if I wanted to, again, use my rules of writing things out, that's going to be 3 times 2 multiplied by itself 5 times, which is 1, 2, 3, 4, 5 threes multiplied together, and 1, 2, 3, 4, 5 twos multiplied together. So the exponential distributes across the multiplication. 3 times 2 all to the 5th becomes 3 to the 5th times 2 to the 5th. And that might show up more often if we have a variable in there. That becomes 2 cubed x cubed, which is 8x cubed. That's how they distribute across multiplication. Division works the same way. But if I tried, let's try to keep this as simple as possible. I think this is going to work. There are exceptions to everything, but I think I'm safe here. 3 plus 1 all squared. Well, that tells, I would do this as 4 squared, which is 16. This is, oops, which is 16. And that's definitely correct. But if I tried 3 squared plus 1 squared, that'd be 9 plus 1, which is 10, and that's wrong. So powers or exponentials do not distribute across addition or subtraction. They distribute across multiplication or division. Whew, we got more. These rules come and they just keep coming. But they all come for that basic idea of powers is repeated multiplication. So we've talked about let's see. Let B be any number. Is it B? Yeah. Let B equal any number. We've talked about raising B to positive powers like B cubed. We've talked about raising B's to negative powers like B to the minus 2. Because of the way this works, B to the 0 will always equal 1 no matter what B is. So that's just a rule to keep in mind. Any base raised to the 0 power is always equal to 1. So we've dealt with positive integers, negative integers, 0. Now let's deal with fractions. So again, our notation is chosen because it makes the rules work. B to the 1/2 is how we write the square root of B. And as soon as we do that, it allows us to use these powers, add them together, subtract them, etc., just the way we did with the integer powers. B to the 1/3 is the cubed root of B, which we write as the root sign with a little 3. And I can combine my powers. I can look at, for example, B to the 7/3. That's going to be the cubed root of B to the 7th, is how we could write it. And as soon as we write it using a fractional power, we can use all those other tools of exponents. And B to the, let's say, 4/5 is the 5th root of B to the 4th. I can put negatives on any of these, and it just switches things into fractions. So now we have whole numbers, negative numbers, 0, fractions, negative fractions follow from that. Any number can be in a power. Any number can be an exponent. We're mostly going to work with whole numbers, positive or negative integers, and occasionally some fractions. We don't work with super crazy numbers. Decimals on occasion, we'll work with those. So B to the 0.7, there's nothing wrong with that. I can ask what is B to the 0.7, because I could write that as B to the 7/10, and then I know that's the 10th root of B to the 7, and my calculator understands both of these, actually all three of these operations. I think that's it for our basic rules of exponents. So now we can start talking about exponential functions. An exponential function is a function that uses repeated multiplication. And we don't really talk about it using repeated division, because if it were division, we could always turn it into multiplication by a fraction. So an exponential function is just a function that uses repeated multiplication. And I'm going to compare and contrast with linear functions, because usually we've spent more time working with linear functions than exponential functions. So here's our linear functions, and here's our exponential. The first thing is I'm going to rewrite what I said up here, which is this is repeated multiplication. Technically, it could also be division, so I'll put that in parentheses. And a linear function uses repeated addition, or if we think of it in a different way sometimes, or repeated subtraction. So they're both pretty basic functions. You just do an arithmetic again and again and again and again. They both have a y-intercept. linear functions have a constant rate of change. Sorry, I don't need to write linear again. Constant, I'm going to write additive or addition rate of change. And exponential functions, they also have a constant rate of change, but it's a constant percent or multiplication rate of change. Now, in a linear function, we call that constant rate of change the slope because it's a line and it's straight. Exponential functions are not lines, so they don't have a slope. So I usually call it the exponential rate of change. Sometimes you see it written as what's called a multiplication factor. So these functions are very, very similar. The only difference is linear functions work through addition or subtraction, and exponential functions work through multiplication or division. So let's write down our basic formula. I'll write the exponential one again, but our basic formula for a linear function is y equals mx plus b. M is our slope, and b is our y-intercept. An exponential function, they could have made it really easy if they used b for the y-intercept, but they didn't. I'm sorry about that. That's what your book says. A here is the y-intercept, and b is the exponential rate of change. So you have to keep track that in a linear function, b is your y-intercept, but in an exponential function, b is your rate of change. It's the thing that's like the slope. All right, I've used a lot of word representations. Now let's use numerical representation. So here's x, and I'm going to give a sample linear function. Y equals 3x plus 2. X equals 0 is always a great place to start. When x equals 0, y equals 2. That's the y-intercept. And then when I add 1 to x, I add 3, and that's the key right there, the addition to the output. All right, linear functions work by repeated addition. Every time x increases, I add 3 to the y. If I increase by x again by 1, I'm going to add 3 to the y again. And every time I increase x by 1, I add 3 to the output. Now let's look at a numerical representation for exponential rate of change. I'm going to pick all different numbers. So 5 times 4 to the x. So a good place to start is with x equals 0. And that means we have 5 times 4 to the 0. And if you remember that rule, 4 to the 0 equals 1. So this just equals 5. That's my y-intercept. That value right there, the a value, is the y-intercept. Now, for an exponential function, I still increase x by 1. I still add 1 to x, but now I multiply y by 4 because I have 5 times 4 to the first, which is 5 times 4, which is 20. I've multiplied my output by 4. Increase x by 1, multiply the output by 4. Let's do it again. Let's increase x by another. And there's my repeated multiplication, 5 times 4 times 4, which is now going to be 80. And if I do it one more time, increase x by 1. I'm going to multiply by 4 again. 80 times 4 is 320. So comparing our two numerical representations, the linear function increases by adding to the output when the input increases. The exponential function changes by multiplying the output when the input increases. Other than that, they're completely analogous one to the other. They both have a y-intercept, they both have a constant rate of change. And so we can use a lot of similar tools to understand them. All right, so we've talked about some verbal ideas. I showed you the symbolic in the table. Now I'll show you what the functions look like on a graph. Let's start with our linear function. I can go ahead and pick this one, y equals 3x plus 2, but I'm going to change my scale just a little bit so I can fit it all. All right, so now one grid is 2 units, not just one. So when x is 0, y is 2. When x is 1, y is 5. When x is 2, y is 8. And I get a straight line. The slope is 3. Over here in the exponential world, I'm quickly going to run out of the ability to show you what this function looks like because it's going to grow so fast. It starts at 5, and in just one step, it's up to 20, and in another step, it's up to 80. So I can't really draw it to scale at all. So I'm just going to show you the shape. Here's where it crosses. There's 5. And then each time the x increases, I multiply the output, and that's going to change faster and faster and faster with every step. So the result is that it curves up toward infinity pretty darn quickly. All right, that's a brief overview of basic exponential functions in all 4 representations. Next, we're going to start using them to answer some questions. And actually, I'm going to give you a couple rules first, what an exponential function looks like. So rules for exponential functions. The first rule is any positive number can be the base, but it has to be positive. Oops, any positive number. So things like 3 times 5 to the x, that's fine because the base right there is positive. Oh, I didn't define the base in the context of a exponential function. So remember I said that if you have 4 to the 3, this 4 right there is the base. The base is the exponential rate of change. So the number you're multiplying by can be any positive number, but it has to be positive. Here's another one that's okay. 7 times 1/4 to the x. That's okay because 1/4 is bigger than 0. Here's one that's not okay. 2 times -3 to the x. Not an exponential function. Yes, yes, no, because -3 is not greater than 0. You could put 0 in, but then it's just a super boring constant function. So we say that exponential functions have to have a positive base, a positive exponential rate of change. Rule 2, the x, or whatever the variable is, must be in the exponent. So 2 times 3 to the x, yep, that's fine, because x is in the exponent. Uh, Another one that would be fine, and you're going to see this a lot when we start talking about percentage changes, might be something like 100 times 1.052 to the x. That's okay because x is in the exponent. This function is not exponential because the x here is not in the exponent. This is called a power function, and it does grow pretty fast, but it doesn't grow through repeated multiplication, so it's not an exponential function. And the final rule is that linear combinations of x are allowed in the exponent. What I mean by that is you could just have a basic exponential, but you could also take that x in the exponential and do something that would work as a linear function. X minus 1, that's a basic linear function. So this is allowed. This is an exponential function. I can do something like multiplying the x by a number. That's okay too, because that's a linear combination, right? 0.03x, that's just a number times x. And I can combine all that even and do something like do 10 times 2 to the 3x plus 4. All of these are versions of exponential functions. And the real reason they're versions of exponential functions is you could rearrange them to look like a times b to the x. Even though they don't look like it right now, you could rearrange all of these to look like a times b to the x. A here is actually not going to be 5, it's going to be a different number, but it still would be a times b to the x. Okay, those are our rules for exponential functions. Let's do some examples where we practice going from verbal to symbolic. Let's see. I love chocolate. And I have a 2-pound bar at home. I want it to last as long as possible. So instead of like eating 1 ounce every day, that would be linear. I eat 10% of it of the bar every day. So 2 pounds is like 32 ounces. So first I eat 3.2 ounces. And then I have to eat a little bit less and a little bit less. And let's make a table to explore this. So X is going to be the day, and Y is going to be the pounds. I'm going to be using Desmos to help me with the arithmetic, because one thing about exponential functions is since they're repeated multiplication, the numbers can change pretty quickly and not in a very standard way. So on day 0, I had 2 pounds. Awesome. On day 1, oh, do we want to do pounds? Sure, that's fine. I was going to do ounces, but pounds is okay. On day 1, I've eaten 10% of it. So it's going to be 2 pounds times the 90% that's left over, which is 1.8 pounds. because I multiplied the two. And here's something that's a little interesting. If I eat 10% of it, I'm not multiplying it by 0.1, I'm multiplying it by 0.9, because if 10% of it is gone, then 90% of it is left. Nevertheless, it is going to be a repeated multiplication. On day 2, so after I increase by another day, it's going to be 2 times 0.9 times 0.9. This is where I'm going to use Desmos to help me. You won't be able to see it, but that's okay. So I'm going to do 2 times 0.9 times 0.9. And I get 1.62 pounds. Then multiply by 0.9. Notice I'm changing my constant multiplication, but the quantity isn't changing the same way. And I go a little bit longer, so I do another. That's 2 times 0.9 times 0.9. But this repeated multiplication is starting to bother me, so I'm going to write it using exponential notation. And I have a 1.458 pounds now because I multiplied it again by 0.9. And I can keep doing this. I keep eating chocolate every day, but I'm only eating 1% of what's remained. Remember I said exponential rate of change is a constant percent rate of change. Let's go a few more days. Let's go all the way up to 7 days. And this is the reason why our exponential notation is useful, because the calculation is really easy to do when you have that nice closed formula. Now I'm down to 0.95 pounds approximately. And I could keep going even more. I could keep going until maybe I've gone 20 days. And now I'm down to 0.24 pounds. But after 20 days, I still have a quarter of my, or well, not a quarter of my chocolate. I still have a bunch of my chocolate left. I could even go up to 100 days. And here I added 20 or so, and then I had 13. And the formula allows me to do that really quickly. And believe it or not, I still have some chocolate. I have 0.00005 pounds. Maybe it's just a little flake, but I still get some chocolate on my 100th day. One key thing about exponential functions is exponential functions or basic exponential functions, where it looks like f of x equals a times b to the x, never touch the x-axis. It's hard to draw by hand because I'm not the best at sketching these. Desmos is helpful, but even with Desmos, it can be hard to tell after a while. I'm going to draw this function we've just been working on. All right, I started at 2 pounds on day 0. And then I went to, and the scale's not going to be quite right, but 1.8 pounds. My next day is going to be 1.62 pounds, et cetera, and I'm going to come down toward the axis, but I'm never going to get there because there's always a little bit of chocolate left. And if it could go backwards in time, I would get more and more chocolate, which is pretty nice. So this exponential function never reaches the x-axis. It gets closer and closer, but it never gets there. All right, how do you build an exponential function? From words, you look for the rate of change. If I eat 10%, I'm losing 10%, so I'm keeping 90. That 0.9 is your multiplication factor, or the repeated multiplication, or the exponential rate of change. And then just by exploring my table representation, I got a really good picture of what that repeated multiplication is. It's 2 times 0.9 to the x. That's going to be my function. Changing percentage to multiplication is one of the challenging things for exponential functions. So I encourage you, when you have the verbal representation, to really talk it through in your head or with a neighbor and decide if the percentage change is 10%, then the multiplication factor in this case should be 0.9. All right, let's do another one. Suppose I have $100 in a savings account, and every year I earn 3% interest. How much money do I have year over year? So again, we look at this and we decide, aha, it's changing by a percentage, so it must be exponential. So let me write down some guidelines for modeling with exponential functions. The first is simply decide if the situation is exponential. Look for a percentage change or a constant multiple or division. If I said every year my money doubled, first of all, I'd be super happy. That's a constant multiple. In this case, it's a constant percent change. And then just write down what your exponential function looks like without worrying about any of the details. I know an exponential function should look like a times b to the x. So write the general formula. This is actually a strategy for modeling with math in general. You have to decide what type of function models your situation, then write the general formula, then identify I'll just call them the letters, usually not x, i.e. not the variable. We really want to identify the other letters. In math speak, these are called parameters. They're important numbers that don't change. Identify the letters in words. We don't have to get what those numbers are yet. Let's just remember what is A and what is B. So A is the y-intercept, i.e. the starting value, and B is the exponential rate of change, i.e. the multiplication factor. Once you've done that, find the values of A and B. Find the values of your parameters from the sentence or sentences, from the words. And suppose I have $100 in a savings account. That's what I started with. So A must be 100. and every year I gain 3%. So, well, does that mean B is 0.03? Or does that mean B is 0.97? Because that's 1 minus 0.03. Does that mean B is 1.03? I've got a lot of options. Figuring out B is the more challenging approach, or the more challenging part of these questions. But until you build your intuition, just test all of them. Okay, let's use the numeric numbers approach to help us. So if I think B is 0.03, then as I increase from 0 to 1, I would be multiplying by 0.03. Oh, gee, that's $3. That's not good. Right, that would say after a year, I have $3. And after 2 years, I'd have, I believe it's 0.9, right? No, 0.09. I'd have 9 cents after 2 years in my savings account. I'm sorry, my cat is trying to get my attention. I'm gonna pause the video. Okay, so using the multiplication factor of 0.03, that's not gonna work. So it can't be that one. What if I used 0.97? Well, after a year, I'd have $97. But that doesn't work either because I'm supposed to be earning interest. I'm supposed to be making money year over year. My balance should be increasing, and this balance is decreasing year over year. So that one doesn't make sense either. And let's try if B is 1.03. I'm going to reuse my space here. I start with 100. After a year, I multiply by 1.03. Aha, there, I have more money now. I've increased by a year and I've multiplied by 1.03. I've increased my balance from 100 to $103. And if I wait another year, I'm going to be multiplying by 1.03 again. So let me grab Desmos to figure out what that is. It's $106.90 because interest compounds. It grows faster and faster and faster. Or you could also say it grows by a constant percentage change. So B should be 1.03. And my formula then becomes f of x equals the $100 y-intercept times 1.03 to the x. And now I can use this to figure out how much money I'd have in 5 years or 10 years or 40 years. Just out of curiosity, let's say I've got $100 to spare, and I'm going to drop it into a savings account. That's pretty low risk, so it only offers me 3% interest per year. After 40 years, I'll have $326. Yeah, that's not going to work. I can't retire today. I'm going to still have to work. It more than tripled the value, but $100 turning into 326 after 40 years, I mean, that's not so fantastic. We can graph this. I want to graph this because it's going to demonstrate a difference between our earlier function. So again, my scale is going to not work so well to make it visible. So year 0, I have 100, and then I have 103, and then I have 106, and then I have a point and 90 cents, and then I'm going to end up with somewhere probably closer to 110, and the constant percentage multiplication is going to increase my money faster and faster as time goes by. Of course, after 40 years, I'm only going to be up to $326. So this again demonstrates that it's really hard to graph an exponential function by hand. This was f of x equals 100 times 1.03 to the x. And this one here this was my other one, which is f of x equals 2 times 0.9 to the x. And the difference is 1.03 is a number bigger than 1. So I'm multiplying and growing. And 0.9 is a number smaller than 1. So I'm we say I'm decaying. So a graph that grows up and to the right is known as exponential growth. And a graph that goes down and to the right is known as exponential decay. But they both work off the same principle. You start with an initial value and you do repeated multiplication. If your multiple is bigger than 1, you grow. And if your multiple is less than 1, but still has to be positive, then you decay. Faster growth leads to graphs that go up faster. Slower growth leads to graphs that grow up slower, but they all bend up in the end. All right. I think that just wraps it up I think that just about wraps it up for exponential functions. I do want to come back to this. What do I do when it's a percentage change? How do I find the multiplication factor? I think using that logic and saying, well, if the percent is 3%, it could be 0.03 or it could be 0.97 or it could be 103. And let me just use a little bit of logic to decide. But it can also be helpful to have a rule. So to convert a percent change to a multiplication factor, step 1, turn the percent into a decimal. Step 2, if the percent change is growth, leave the decimal positive. Well, yeah, I'm going to put that in parentheses. If the percent change is growth, add the decimal to 1. Right, we had a 3% growth, so we added 0.03 to 1, and we got 1.03. If the percent change is decay, subtract the decimal from 1. And that's your multiplication factor. So I'll give you 3 examples. 3% growth becomes 0.03, and we add that to 1, and we get 1.03. 10% decay, right? Like if I eat 10%, that's going to be 0.10, and I'm going to subtract that from 1, and I get 0.9. And then the hard one is, let's say every day, 70% is left. Okay, well, if every day 70% is left, then this is kind of an exception. Then my multiplication factor is just 0.7 because every day 70% is left. So if it's every day remove 10%, that's 10% decay. So you subtract it to get 0.9. But if you have every day 70% is left, that's 0.7. Because the multiplication factor is always what you have left after a time period. All right, that wraps up this video. Thanks for watching.